Too many unanswered questions. I agree. And then, of course, we have Chapter 4, this black hole at the beginning of time. A spacetime singularity. Imagine the questions that have troubled the greatest minds for centuries, mysteries that stretch our understanding of space, time, and existence itself. These are the questions that keep astrophysicists up at night. Let's unravel them, one by one. Planets, stars, galaxies, everything visible makes up less than 5% of the universe. The rest? It's dominated by dark matter and dark energy, comprising about 25% and 70% of the universe, respectively. Dark matter is unlike anything we can see or touch. It doesn't emit, absorb, or reflect light. Its existence is inferred through its gravitational effects on visible matter. Without dark matter, galaxies would fly apart. The gravitational pull from visible matter alone isn't strong enough to hold them together. This invisible substance exerts a gravitational force, shaping the universe's structure. We detect dark matter through its gravitational influence on light, which bends in response. This bending, known as gravitational lensing, acts as a cosmic magnifying glass, revealing dark matter's presence. While we can't see it directly, its interaction with gravity confirms its existence in vast quantities. Dark energy, on the other hand, is even more elusive. Its effects are evident in the universe's accelerated expansion. In 1929, Edwin Hubble discovered that distant galaxies were receding faster than closer ones, a phenomenon revealed by the redshift in their light. Contrary to previous beliefs, the universe's expansion isn't slowing down, it's speeding up, driven by dark energy. This mysterious force, which makes up most of the universe, acts in opposition to gravity and seems intrinsic to space itself. As space expands, dark energy strengthens, continuously generating more space. It's not a physical substance but a property of space itself. Although we have several hypotheses, from exotic particles to space's inherent properties, no theory fully explains dark matter or dark energy yet. This frontier of science is understandably frustrating but also marks the boundaries of our current knowledge. Exploring these cosmic mysteries reveals just how much we have yet to learn, reminding us that we are merely beginning to navigate the immense cosmic ocean. Among the most unassuming substances that hold keys to great mysteries is antimatter. Far from just a science fiction concept, antimatter presents one of physics' most perplexing puzzles. Why does anything exist at all? For every particle, there is an antiparticle, a mirror opposite in charge and spin but identical in other respects. Electrons have positrons, protons have antiprotons. When matter and antimatter meet, they annihilate each other, releasing pure energy in the form of photons, leaving nothing behind. If this perfect symmetry held, the universe would have self-destructed after the Big Bang, leaving only light, but matter exists, we can touch it, see it, live in it. So, why is there more matter than antimatter? This imbalance, known as the matter-antimatter asymmetry problem, suggests that during the universe's inception, conditions slightly favored matter over antimatter. For every billion pairs of particles and antiparticles that annihilated, one matter particle remained. This small asymmetry allowed the universe as we know it to exist. This slight preference for matter over antimatter implies a fundamental asymmetry in the laws of physics, particularly how the universe treats matter and antimatter. While the standard model of particle physics is incredibly successful, it doesn't explain this asymmetry. Experiments at CERN, such as the ALPHA experiment and ELENA facility, aim to trap antihydrogen and compare it to hydrogen, probing the very foundations of modern physics. These experiments don't just test antimatter's properties, they challenge the symmetries of space and time itself. Our current models of physics are incomplete. They falter at explaining why the universe prefers matter, why we exist, and why there is something rather than nothing. The observable universe, spanning 46 billion light-years in all directions, is just the beginning. Beyond this boundary lies the unobservable universe, perhaps infinitely larger and unreachable due to the limits of light and time. What could lie beyond? The universe might extend endlessly, with an infinite number of galaxies, repeating patterns of galaxy clusters and voids. Alternatively, if the universe curves back on itself like a higher dimensional sphere, traveling far enough in one direction might bring you back to your starting point. This closed universe would be both finite and borderless. As the universe expands, driven by dark energy, galaxies recede faster than light can travel, sealing off the far reaches of the cosmos. These realms remain hidden, forever beyond our view. Black holes are among the universe's most fascinating objects. At their center lies the singularity, where gravity becomes infinite and the known laws of physics cease to function. Crossing the event horizon, the point of no return, leads to a place where space and time swap roles. All paths lead inevitably to the singularity, where traditional dimensions of space and time collapse. At the singularity, density and gravity reach infinite levels. The crushing forces would disintegrate any matter approaching it. General relativity describes black holes using only three properties: mass, charge, and angular momentum. Yet, the black hole information paradox arises, as quantum mechanics dictates that information cannot be lost. When matter falls into a black hole, the information paradox suggests that information disappears, a direct contradiction to quantum theory. Venturing beyond the event horizon leads to speculative theories. Some suggest black holes might be gateways to other parts of the universe or even to entirely different universes, akin to wormholes. But these ideas, while fascinating, remain unproven. The singularity challenges the very fabric of our understanding. The story of everything we know begins with the Big Bang, not an explosion in space, but an expansion of space itself. The universe, once infinitesimally small, hot, and dense, has been expanding ever since. From this fiery beginning came the structures of stars and galaxies we see today. Despite recent discoveries, including those from the James Webb Space Telescope, evidence supporting the Big Bang remains strong. As the universe expanded, it cooled, forming the protons, neutrons, and atoms that make up everything we see. An important clue to this early universe is the cosmic microwave background radiation, a relic from 380,000 years after the Big Bang. This faint glow gives us a snapshot of the universe's birth. Though the Big Bang explains much, it also raises profound mysteries. What preceded it? Is our universe unique, or one of many in a vast multiverse? These questions push the boundaries of our knowledge and hint at new laws of nature yet to be discovered. As we explore, we peer back in time, drawing closer to that primordial moment of creation.